Rate laws. The concentrations of reactants decrease as a reaction proceeds. How the reaction rate changes due to the change in concentrations, if the rate changes at all, depends on the reactant and the reaction. The formula that describes how the reaction rate changes for a reactant based on its concentration is called the rate law. Each reactant in a reaction has its own rate law. They are not necessarily the same, even in the same reaction. And here's the key thing. They can only be determined experimentally. They are not related to the coefficients in the balanced equation for the reaction. The reaction rate R is defined by the following expression, in which bracket A is the concentration of reactant A and T is time. The delta indicates the change of. The minus sign ensures that R will be a positive number, since delta A will always be negative, since the reactant concentration is decreasing. And delta T, of course, is always positive. So read this reaction as the reaction rate is equal to the negative of the change in concentration of a reactant divided by the change in time. Zero-order reactions maintain the same rate over time. Their rate does not change as the concentration of the reactant is reduced. Their rate law is rate equals K. Rate is the reaction rate and K is the rate constant. There are no variables in this law. The rate is just the constant K. Therefore, its graph is a line with a y-intercept of the initial rate and a slope of 0, as shown here. Right? This shows that the rate stays the same as the reaction proceeds in time. It's a constant value right there. With a constant reaction rate, the concentration of a reactant will linearly decline over time. We will use bracket A to represent the concentration of reactant A at any time. So that would be the y-axis here. And bracket A0 is its initial concentration. That's that point right there. That is bracket A0. Then the concentration over time is this equation. Bracket A is equal to bracket A0 minus KT, which is the equation of a straight line. It has a y-intercept of bracket A0 right up there, and a slope of minus K. That's the slope of this line here. Since K is constant, so is the slope, which is why it's a straight line. Let's switch back to a rate time graph to describe a first-order reaction. First-order reactions slow at a steady rate over time as the concentration of the reactant is reduced. The reaction rate is proportional to the concentration of the reactant, which declines over time. And here's our first-order rate law. It's equal to K times the concentration of A, or bracket A. This is a linear equation with the rate declining as the concentration of the reactant declines. The y-intercept is the initial rate, and its slope is minus K. Now let's show the graph of the concentration of a reactant in a first-order reaction over time. The slope of the curve at any time is equal to the reaction rate at that time. As the reaction rate declines over time, the slope flattens out. See, you get close to 0 down here. That is unlike the slope of the zero-order reaction, which is constant. Second-order reaction rates are proportional to the square of the concentration of the reactant. As a result, they initially slow down more rapidly, up here, as compared to first-order reactions, but then the reaction rate declines more slowly down here. The second-order rate law is rate is equal to K bracket A squared. Let's switch over to the concentration graph for a second-order reaction. As in first-order reactions, the reactant concentration declines with time and the reaction rate and slope of the curve declines over time. The difference between the graphs for first and second order is more subtle. The concentration drops more quickly at first, but then takes longer to reach 0 down here. Rate laws are determined for each reactant by measuring how its reaction rate changes as its concentration changes over time. That determines its reaction order, which then allows the reaction constant to be determined. So here's a summary. Here's our zero order. The rate is just equal to K. First order rate is equal to K times the concentration of A, and second order rate, K times the concentration of A squared. So you go from a horizontal line, a linear line decreasing here, and then this curve here, 1 over x type curve. Reaction rates are not directly measured in the laboratory. Concentrations are measured. Then, the rate at any time is calculated from dividing the change in concentration by the elapsed time. Let's work an example. The rate of the gas phase decomposition of dinitrogen pentaoxide at 45 degrees Celsius is shown in the chart. We can follow changes in molar concentrations over time to learn about the reaction. The concentration of N2O5 is plotted versus time, and some analysis has been provided here. This was done in a lab. Analyze the information on the chart and determine the rate law for N2O5 in this reaction. So we show the concentration that was measured, and now we determine the rate law from this chart here. The rate of the reaction decreases by half when the concentration of N2O5 has decreased by half. So here's the rate at this point, 5.4 times 10 to the minus 4th moles per liter second, and that's the slope of the line at that point. And here's your other rate, which is half, right? 2.7 is half of 5.4. Let's look at the concentrations. Here, it's about 0.90, and down at this point, it was about 0.45. Right, so that's why we could make this statement here. Since the rate declines in proportion to the concentration, the rate law is rate equals K times the concentration of N2O5. The reaction is first order with respect to N2O5. Note, the coefficients of the equation do not tell us the order of the reaction. The order has been determined experimentally. Right, because here's the coefficient 2, but we have a first order here. A rate law shows the relationship between the reaction rate and the concentrations of reactants. The exponents tell us the order of the reaction with respect to each reactant. Every reaction has a specific rate constant K that varies with temperature. For a reaction with one reactant and a rate order M, the rate is Ka, concentration of A, raised to the M power. So for this reaction here, right, the N2O5 turning into nitrogen dioxide and oxygen, the rate is K times N2O5 period. M is equal to 1. Okay, so there's no exponent there. Every reaction has a rate constant K that varies with temperature. For any reaction, AA plus BB that turns into products, where A is the coefficient of your molecule or your atom, there's a rate law involving K. Your rate will be K times concentration of A raised to the M power times the concentration of B raised to the N power. M and N are orders of the reactants. The rate of a reaction is equal to the product of the rate constant and the concentrations of the reactants raised to their respective orders. And note, little a, which are the coefficients, and little b, they don't play into this at all. Experimental data show that the decomposition of ammonia to nitrogen and hydrogen gas is second order with respect to ammonia. And here's the data that was used. As the concentration of ammonia is halved, the rate of the reaction decreases to 1/4. Well, let's see where we got that from. Let's take this point here and this point here. Now notice, that isn't exactly half, right? It would have been great if we had a point here that was 0.0022, but we don't. So we're going to have to approximate this. So let's look at the rate. It went from 8 down to 1.8. That's pretty close to 1/4, so that's why we're making this statement here. In the reverse reaction, that's when you go in this direction, and we'll take the same 2 points. As the concentration of ammonia doubles, the rate of the reaction quadruples. So we have this rate law. This is a second order rate here. So rate is equal to K times the concentration of ammonia squared. Aqueous ammonia and nitrite react to form nitrogen gas and water. Comparing experiments 1 and 2 shows that when the concentration of ammonia doubles, right, goes from 0.01 to 0.02, the initial rate doubles, goes from 5.4 times 10 to the minus 7th to 10.8 times 10 to the minus 7th. The reaction, therefore, is first order with respect to ammonia. Now let's compare experiments 5 and 6 for nitrite. That shows when the concentration of nitrite doubles, the initial rate doubles. Right? You go from 21.6 times 10 to the minus 7th to 43.3 times 10 to the minus 7th. The reaction is first order with respect to nitrite. The rate of reaction is proportional to the concentration of each of the reactants. And that's the Greek letter alpha, which means proportional to. These two proportions can be combined into one. The rate is proportional to the concentration of ammonia times the concentration of nitrite, which can also be written, you can replace a proportional sign by putting a constant in there. In this case, that'll be our rate constant. So the rate equals K times the concentration of ammonia times the concentration of nitrite. Because the data show that the reaction is first order with respect to ammonia and first order with respect to nitrite, the exponents on the reactant concentrations are 1 and 1. And typically you just leave that out if it's a 1. The overall reaction order can be found by adding the exponents on the reactants in the rate law. So in this case, we have 1 plus 1 is equal to 2. That means the reaction is second order overall. If the concentration of either reactant is doubled, the reaction rate will double. If the concentration of both reactants is doubled, the rate of reaction will quadruple. We have another reaction here. Nitrogen oxide plus hydrogen yields nitrogen and water. The reaction is second order with respect to nitrogen oxide and first order with respect to hydrogen. That was determined experimentally. Even though 2 molecules or moles of each nitrogen oxide and H2 hydrogen are reacting in above the reaction is not fourth order overall. Once again, the coefficients are not related directly to the order of a reactant or reaction. The order of a reaction is determined only experimentally. You cannot predict it without observing in some way the actual physical manifestation of the interactions of particles in the reaction. Experiments have shown that the reaction is second order with respect to nitrogen oxide and first order with respect to hydrogen. Therefore, this is a third order reaction overall because 2 plus 1 equals 3. If the concentration of nitrogen oxide is doubled, the rate of the reaction will quadruple. If the concentration of hydrogen is doubled, the rate of the reaction will double. If the concentrations of both reactants is doubled, the rate will increase by a factor of 8. And just one more time, don't look at the coefficients to determine the order of the reaction. That can only be determined experimentally. So here's our final rate equation for this reaction.